Good afternoon, ladies and gentlemen. Welcome to this presentation on expansion of functions into power series under the course EGM 212, which is Engineering Mathematics 2. So an infinite series that takes the form, the sum of the product of CK, open bracket, x minus a raised to the power k is expanded as shown on the right-hand side of the equal sign. So this normally is the sum of the product is denoted by the Greek symbol sigma. So this the values of k are being taken from 0 to infinity. So the sum of the product of CK and x minus a in brackets raised to the power k is what gives the expansion on the right-hand side of the equal sign. So this is an infinite series because it continues. As you can see at the extreme end, there are 3 dots. Those 3 dots imply that the series continues. It continues. There are infinite values that are not shown at the end there. Okay, so an infinite series of the form sigma ck open bracket x minus a close bracket raised to the power k, taking values of k from 0 to infinity is given as the expression on the right hand side of the equal sign. This kind of infinite series is known as a power series in X, or simply a power series. And the constants, the CK here, where the values of K are ranging from 0 to infinity. These C's, you have C0, C1, C2, C3, and it goes on and on and on. So the constants C0, C1, C2, C3, and so on are called the coefficients of the power series. And the constant A, there's this A which is appearing in the formula or in the expression. That A is called the center of the power series. So the A is called the center of the power series. So a power series in X with the center A is equal to 0 takes the form as shown. So if in this expression up here, the value of A is equal to 0, then the resulting expression looks like this. So we have the sum of the products of CK, then X raised to the power K. So we keep multiplying the product, we keep on adding the products of CK and X to the power K for every particular value of K ranging from 0 to infinity. So this expression on the right-hand side of the equal sign is what generalizes the idea of a polynomial in which x is the variable. So this is, as we can see, we have CO plus C1x plus C2x squared plus C3x cubed, and the values of the powers of the variable x keep increasing. So on the first term, the value of the power of x is 0. Then the power of x here is 1, then 2, just like that, to infinity. So this then is the generalization of the idea of a polynomial in which x is the variable. So let's look at what is known as Taylor's series. Taylor's series. Okay. So let's assume a function f of x to be having a derivative that is fn, the subscript, the superscript rather, n there, is implies how many times the function has been differentiated. Okay, so we are saying this function is having a derivative fn of the order n is greater or equal to 1 on an open interval I, and let a be a fixed number in I. Then the nth degree Taylor's polynomial for the function f at the number a is the polynomial function that is shown. So we'll say that again. Let f of x be a function having a derivative fn of the order n greater than or equal to 1 on an open interval I, and let a be a fixed number in an interval I. Then the nth degree Taylor's polynomial for the function f at the number a is the polynomial function here, this one shown. So Pn of x is equal to f of a plus f prime a over 1 factorial open bracket x minus a close bracket plus f double prime of a over 2 factorial, then open bracket x minus a squared plus, so there are some terms here. These 3 dots indicates that there are several terms in between here. Then plus f, then n. So this n implies how many times the function has been differentiated. Then having differentiated that, you replace the value of x by a, then divide by n factorial, then multiply by x minus a raised to the power n. Okay, so this expression can also be written as this. There's no difference. We've just moved the x minus a squared, x minus a to the power n. We've moved it to the numerator part. So it's just one and the same. This is just another way of expressing that. So this expression we've indicated is what we call Taylor's series. It's known as Taylor's series. Sometimes we call it Taylor's formula or Taylor's theorem. So this expression is very important. Let's remember how it is written. Okay. So let's look at one term that I used in trying to describe this expression. I'm sure some of you do remember. On the denominator part, there are these terms. The second term in the expression on the denominator part has got 1 factorial, 1 with a symbol like an exclamation mark. So that exclamation mark is read as factorial. So this is 1 factorial, 2 factorial, then n factorial. Okay, so now let's come here. Recall that if n is a positive integer, then n exclamation mark, which is read as n factorial, is defined by n factorial is equal to n multiplied by open bracket n minus 1, we close the bracket, then again multiply by open bracket n minus 2, we close the bracket. Then there are several values here. We keep on reducing by 1. We keep on reducing the given number by 1 until you get to 1. So n factorial is equal to n open bracket, n minus 1, close bracket, then again, open bracket, n minus 2, close bracket, dot, 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 3 multiplied by 2 multiplied by 1. So if you have a number like 5 factorial, 5 factorial would mean 5 factorial, 5 factorial would mean 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So 5 factorial is 5 multiplied by 4 multiplied by 3 multiplied by 2. So 5 by 4 is 20. 20 by 3 is 60. 60 by 2 is 120. So 5 factorial is 120. This is very, very simple. Then there is also another one, which I'm sure you do remember. By definition, we say 0 factorial is equal to 1. Okay? I think from the lower course, EGM 211, you must have been introduced to these concepts. Okay? So this is Taylor's series. Let's look at some worked problems that involve the application of Taylor's series. Number 1, use Taylor's formula to expand the function f of x is equal to x over x minus 1 about the point a is equal to 0, and your expansion should go up to the 4th term. Solution. First thing, we are given the function f of x is equal to x divided by x minus 1. So the first step, where there is x, we put the value of a. Where there is x, we put the value of a. So the first step here, we are simply replacing where there is x in the given function by the value of a. So a over 2 minus 1 is equal to 2. So this is the first term. Then the second is finding the differential coefficient of this function. So differentiating it once, if you differentiate with respect to x, it will give us negative 1 over open bracket x minus 1 close bracket raised to the power 2. So this is the first differential coefficient of the function. Then, having got the first differential coefficient, we again replace the value of x by 2. That is after differentiating it. And after replacing, careful replacement, you find that it will give you the f prime open bracket 2 close bracket. This will give us negative 2 as the answer. Then again, we find the second differential coefficient, the same function after this was the first time we differentiated. Now this same function, we differentiate it again. Differentiating it again, we come to this stage. So after differentiating it again, we get the function 2 open bracket x minus 1 close bracket raised to the power negative 3. Then in this second derivative, where there is x, we put 2, and it gives us 2. Then we get back to the second derivative and differentiate it for the third time. After differentiating for the third time, we get the function negative 6 open bracket x minus 1 close bracket raised to the power negative 4. So in this function now, where there is x, we put 2, and it gives us negative 6. So where do we go from here? We now simply plug it into the Taylor's formula. since we already have an expression. So in that expression, we just start now plugging in the values. Those different values we are finding, just put them in, and after careful simplification, it will give us f of x is equal to 2 minus open bracket x minus 2 close bracket plus open bracket x minus 2 close bracket squared minus open bracket x minus 2 close bracket cubed. Okay, so this is according to the question, because the question instructs us that we need to find the fourth term. So this is the first, second, third, and fourth. So this is up to the fourth term. Okay, so this is the first example. Let's move to the second example. Write down Taylor's formula at the point a is equal to -1 for the function f of x is equal to x to the power 4 minus 2x cubed minus 3x squared minus 4x plus 1. Solution. Similar procedure. We first replace the values of x in this function by -1, because we're putting in the values of a to get the first term. So where there is x, we put -1. This is the stage. Then we move to the second stage. The second stage is to find the differential coefficient. So f prime, this is f prime, the differential coefficient of the given function. So differentiating the given function with respect to x, we get f prime x is equal to 4x cubed minus 6x squared minus 6x minus 4. So this is the differential coefficient of that function. Then, where there is x in the first differential coefficient, we replace it by -1, which is the value of a as given in the question. So after a careful replacement, you find that it gives -8. Okay, so we keep this value. Then we again continue from the first differential coefficient, we move to the second differential coefficient. We have to differentiate the function 4x cubed minus 6x squared minus 6x minus 4. We differentiate it again to get the second differential coefficient, which is f double prime x is equal to 12x squared minus 12x minus 6. Okay, so in the function f double prime x is equal to 12x squared minus 12x minus 6, where there is x, we put -1, and it gives us 18. We continue from the second differential coefficient, we get our third differential coefficient. We differentiate it again to get 24x minus 12. Then in the function f triple prime x is equal to 24x minus 12, where there is x, we put -1, and it gives us -36. Okay, so we again move from the third differential coefficient, we move to the fourth differential coefficient. We differentiate it again to get 24. Then if we replace where there is x, we put -1, of which we don't have x, so the value of 24 is returned. Okay, then next we simply plug in the values. We simply begin to replacing the value. So the expansion of this function will thus be equal to 5 minus then 8 open bracket x plus 1, we close the bracket, plus Then on the numerator part, 18, open bracket x plus 1, close bracket squared over 2 factorial minus, then on the numerator 36, open bracket x plus 1, close bracket cubed plus 24, open bracket x plus 1, close bracket raised to the power 4 over 4 factorial. Then after careful simplification, you get 5 minus 8, open bracket x plus 1, close bracket plus 9, open bracket x plus 1, close bracket raised to the power 2, minus 6, open bracket x plus 1, close bracket raised to the power 3, plus open bracket x plus 1, close bracket raised to the power 4. So this becomes the expansion of the function. Okay, let's move to the third question. I think the procedure is quite straightforward. The key thing to do is to master the general expression of the Taylor's series. Question number 3. Find Taylor's second order polynomial for the function f of x is equal to the root of x at the point where a is equal to 4. So the solution, P2 of x is equal to f of a plus f prime a, then open bracket x minus a, close bracket, plus f double prime a over 2 factorial, open bracket, x minus a squared. So this is just the general expression of the Taylor's expression. So now, having written down the general expression, we can now start looking at term by term. So the first term is f open bracket a, or f of a, which gives 2. Then the first differential coefficient of the given function, it gives 1 over 2 multiplied by the root of x. Then, where there is x in the first differential coefficient, we put 4, and it gives us 1 over 4. So after getting 1 over 4, we leave it there and find the second differential coefficient. So the second differential coefficient is 1 over 4 multiplied by under the root x cubed. Okay? That's negative. Negative 1 over 4 multiplied by under the root x cubed. So this is the second differential coefficient. So in this second differential coefficient, where there is x, we put 4, and it gives us negative 1 over 32. Okay, so having gotten these different values, we simply plug them into the Taylor's expression. So we have P2x is equal to 2 plus 1 over 4, then open bracket, x minus 4, then minus 1 over 32, then x minus 4 in brackets squared over 2 factorial. Yeah, so the instruction is that it has to be a second order polynomial. So we have to ensure that the value of x does not exceed the power of 2. Okay, so the expression on the right hand side is what is needed. 2 plus 1 over 4, open bracket, x minus 4, close bracket, minus 1 over 64, open bracket, x minus 4 squared. Okay, so this is the required second order polynomial. Now we've tackled 3 important examples to shed more light on the application of Taylor's series. Now let's move to another very important series known as Maclaurin's series. Maclaurin's series. Okay? Definition. The Taylor's series for the function f of x at a is equal to 0 is called the Maclaurin's series for the function f of x. So whenever the a, the one we called the center, is equal to 0, whenever a is equal to 0 in the Taylor's series, know that we are talking about Maclaurin's series. Okay, so Taylor's series is given by the expression shown. So here we are stating to say when the value of a is equal to 0, it's no longer Taylor's series, but now Maclaurin's series. So in this Taylor's series, if we replace a by 0, we're going to have Maclaurin's expression, which looks like this. So f of x is equal to f of 0 plus f prime 0, then x plus f double prime 0 x squared over 2 factorial plus f triple prime 0 multiplied by x cubed over 3 factorial plus dot 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 plus f nth derivative of 0 multiplied by x to the power n over n factorial. So this is the Maclaurin's series. So Taylor's series and Maclaurin's series are very much linked. So the only difference is that where there is a in the Taylor's series, we replace it by 0 for us to come up with a Maclaurin's series. Okay. Let's look at some worked problems involving Maclaurin's series. Worked problems involving Maclaurin's series. Let's do a small change here. Okay, worked problems. Find the Maclaurin series expansion for the function 1 over x plus 1 as far as the term x raised to the power 4. So solution. First thing, where there is x in the given function, we put 0 to get a 1. Then we get the first differential coefficient of the function with respect to x. It gives us negative 1 over open bracket x plus 1 close bracket raised to the power 2. Then where there is x in the first differential coefficient, we put a 0 and it gives us negative 1. Then we differentiate again to get the second differential coefficient. It gives us 2 over open bracket x plus 1 close bracket to the power 3. Then where there is x in the second differential coefficient, we put a 0 and it gives us a 2. Then from here, we differentiate again to get the third differential coefficient, which gives us negative 6 over x plus 1 in brackets to the power 4. Then, where there is x in the third differential coefficient,